Done. Recording is started. Now I'll look at. Hi everyone, welcome to the QML presentation, Quantum Machine Learning, and this is organized by Philadelphia section of IEEE, along with AIML, along with the AIML group from INGR, along with QIT, our own, that is the one who is the leading here, and the other one is, of course, Emerging Open Tech Foundation. So these are the four sponsors, and then there are other webinars which are there scheduled for August 2025. And here are the four people, and with that, I will hand over to Ba Chang, who is the co-chair of INGR AIML working group, who is the lead in this, to start with for the AIML portion. Go ahead, Ba.
Thank you very much, Prakash. Thank you very much. My name is Bao Chung. As Prakash mentioned, I co-chair the AIML working group, and we are very happy to be able to support the Quantum Information Technology Working Group in organizing this panel webinar on quantum machine learning. With that, if I don't mind, Prakash, please advance to the next slide.
Yeah.
Okay, these are the biographies of the panelists. I'm not sure I should read through every one of them just because it's a lot of text and it's pretty dense. So primarily, that's myself, Bao Chung. Like I said, I co-chair the Artificial Intelligence and Machine Learning Working Group. There's Chintan Oza, who I'm pretty sure you'll hear from later. He is a co-chair of the Quantum Information Technology QIT Working Group. Next slide, please. And Professor Gokhail Jahanti is the president of Emerging Open Tech Foundation, a co-sponsor of this webinar. And then, of course, you heard from him just now, Mr. Prakash Ramachandran, the co-chair of the Quantum Information Technology, as well as the Edge Service Platform Working Group. So these are your fellow neighborhood-friendly panelists. This is the QML Quantum Machine Learning panel webinar. Again, this abstract has been published before, and because of the very dense text, probably it's not worthwhile to read through the entire text screen. But just say that we'll discuss classical machine learning. We'll talk about corresponding use cases, examine how quantum machine learning can reduce the computation time to solve some NP problems, possibly problems that could not be solved by classical computing. We'll talk about classical models, supervised vector machines, various neural networks, other distinctions from and how they are distinct from their QML counterparts. We'll talk about utilities, tools, code developments, ranging from Qiskit to PennyLane and various other important tools to support QML development, large language models, multimodal learning, etc., etc. Next slide, please. As a quick introduction to the future network technical community, we mentioned before that this webinar is co-hosted, co-organized by the QIT working group as well as the AIML working group. We're all part of this Future Networks Technical Community, the FNTC. The Future Networks Technical Community itself is organized under IEEE with 9 supporting technical societies. And under the Future Networks Technical Community, we have a bunch of other committees. And one of them is the INGR, the International Network Generations Roadmap. And we are part of the working group under the International Network Generations Roadmap. Next slide, please. Now, the FNTC, the International Network Generations Roadmap, has 15 working groups. So AIML is one of them. Quantum Information Technology has been newly established in late 2024. Apart from these two, there's also the Application and Services Working Group, Connecting the Connect Working Group, Deployment Working Group, Edge Services, Energy Efficiency, Massive MIMO, Millimeter Wave Working Group that has since been renamed to Megahertz to Terahertz Working Group, Optics Working Group, Satellite Working Group, Security and Privacy, Standardization, System Optimization, and the Testbed Working Group. So all in all, we have 15 working groups. Next slide, please. And the International Network Generations Roadmap is our flagship publication. This is a technical document that we update every 12 to 18 months. We may stretch it out to a 2-year cycle starting next year. The last edition is the 2024 edition, has 11 topical chapters, the IML, application service, etc., etc. all you can see a list of 12 chapters here. Slight exception for the quantum information technology chapter, in the sense that because it's new, it doesn't quite have a complete chapter, but a white paper listed among the chapters nonetheless. It focuses on technology roadmap for 10+ year horizon. The FNTC does a few things, including things like flagship conferences and events. So the Future Networks World Forum is our flagship conference. For 2025, it will happen in Mangalore, India in November. And the Connecting the Unconnected Summit will also happen at the same place around the same time at 12th November. And of course, there's the Connecting the Unconnected Challenge. It's a global competition that solicits solutions from startups, grassroots organizations, universities, and anyone else that is working to bridge the digital divide in innovative ways. Now, back to AI/ML and quantum information technology. AI/ML and quantum information technology, those are the two most popular topics that I have observed while attending the World Forum back in 2024. You can see on the screen here, I have a statistics on how many papers and keynotes and symposia and such that are focused on AI/ML. I didn't quite take accurate count on quantum-related topical presentations back in 2024, but just based on observation, I'm fairly sure that AI/ML and QIT are the two most popular topics in World Forum back in 2024. Next slide, please. And since I am the co-chair of the AI/ML working group, a quick introduction for the working group itself. As mentioned before, we are part of the Future Network Technical Community organized under IEEE CommSoc. We provide roadmap based on research and industry advancements to deliver the AI/ML vision for the networks of the future. We care about AI and machine learning as they relate to networking and telecommunications. We care about architectures and frameworks to support AI/ML workloads for different domains. And most importantly, we anticipate AI/ML challenges and developments over multi-year horizons. We organize things like webinars, industry outreach forums, conferences, etc. On average, we do one webinar per month. Some of them will be co-hosted or co-sponsored by the IEEE Philadelphia sections, and in this case, co-hosted by the Quantum Information Technology Working Group, and sometimes we do co-hosting with other working groups as well. Anyone interested in joining this working group, again, please feel free to write to the co-chairs at the email address given on screen here. Next slide, please. Regularly, we hold two regular meeting series every first Thursday of every month at 6 p.m. Eastern Time and every third Thursday of every month at 12 UTC. Hopefully, this will be friendly. This will be able to accommodate people in different time zones across the globe. We organize other events and hot meetings as noted in our public calendar, which you can see if you visit our working group webpage. Our working group webpage URL is listed at the bottom of the screen, or you can just scan the QR code to get to our working group webpage. There you will see links to our public calendar that you can subscribe to or follow just to see what events and what meetings we hold. Okay, thank you very much. Next slide, please. Yep, I think I'll hand the floor over to Prakash.
Hi, thank you very much, everyone. And I think I will defer this to panel member Chintan Oza. Chintan, go ahead. Start with this.
Thank you so much. Thanks,
Thank you, Bob.
Thanks.
Thank you, Bob. Yeah. Thank you.
Thanks, Bob. Thank you, Prakash, for leading us and hosting this webinar. Indeed, it's my pleasure being here. I hope I am adequately audible to all of you.
Yes.
We are using the same slide, so no need to check the slide. So, indeed, it's my pleasure to be the founding co-chair for QIT. This is where we were passionate about starting something within INGR, and we are thankful to our leadership for giving us this opportunity. And QIT was formed in September 2023, so we're like kind of 2 years old maybe. But yeah, my dear friends, it's not just 2 years. We have got a lot of things which we have achieved with support of everyone. We did IEEE Quantum Week presentation in Seattle. We conducted a workshop. We also presented during Future Network World Forum 2024, which was held last year in Dubai. We are going to launch a state of quantum computing report 2025 this year, for which we have begun the survey. As and when you get the link, I request you to kindly fill up the survey. help socialize with like-minded people so that we get a larger sample size and we can publish an insightful outcome in the report. This is the right time to have this discussion. Can you go back one slide? This is the right time to have this discussion because 2025, this year, is declared as year of quantum computing. And last but not the least, with this slide, while we move to the next slide, I would also like to mention that I look forward to meeting you all in FNWF 2025, which is being held in Bangalore. So let me quickly share the goals of Quantum Information Technology Work Group. What we are doing is we are collaborating within INGR, cross collaboration with EIML, security, SATCOM, optics work group is going on. We have attended various conferences to help people know about our work group and then spread awareness about quantum computing as a technology. We are focused around generating content as well. 2025 to 2035 roadmap was prepared and it is ready for release. We are attending various events and just like this one, we are also trying to focus and bring awareness and bring various type of expertise on board by hosting various webinars on QML, PQC, QKD, and quantum internet during next 1 year. So stay tuned and also please let myself or Prakash know about joining a webinar, or even if you would like to host one like the one which we are having, please feel free to ping us. We are also building an ecosystem of partners around us. Like we are very happy to have eOTF, Emerging Open Technology Forum, as our partner, Anantam Ecosystems, Maxwell Technology Labs, BITS, RDCU, and IITB. So we are actively collaborating with these institutes and spreading the knowledge, and Quantum Information Technology Work Group is spreading wings in these organizations. Next slide, please. So let us have a look at the QML realms. There are majority two type of data. QML can be broadly divided into four primary sectors, each defined by how we combine these computing resources. So whether we represent quantum computing device as Q or classical devices C, the type of data involved, whether generated by a quantum or classical system, can be classified into four quadrants. These quadrants are CC, that is classical data and classical algorithm devices. QC, which is quantum data typically or originating from some physics experiments working on algorithms or on devices. CQ is classical data handled by quantum computers. And last one is QQ, where quantum computers work directly on data generated by quantum computer. This is the ideal situation we all aim for. This discussion primarily focuses on CQ category. CQ is classical data handled by quantum computers. Let's move to the next slide. Let us look at classical machine learning. Classical machine learning is a way for computers to learn from data and make predictions without being directly programmed for every possible answer. Classical machine learning uses mathematical models to recognize patterns that can be applied to solve problems. The first one could be learning from examples. The computer studies past data and predicts the outcome. Training and testing. It learns from some data, which is also called as training data, and checks how well it performs on the new data, which is also called testing data. And third part is algorithms. Classical machine learning uses models like decision trees, supports various vector machines and neural networks to make predictions. Next slide, please. Let us have an overview and introduction to quantum machine learning. Because we are in a learning environment, we are in an IEEE event. Let us visit the definition. So quantum machine learning is the intersection of quantum computing and machine learning, leveraging quantum principles to enhance computational efficiency. Look at the keywords. Intersection of quantum computing and machine learning, leveraging quantum principles to enhance computational efficiency. Efficiency is the keyword here. Why do we need QML? We need to speed up various complex machine learning tasks. We also need to have potential breakthroughs in optimization and data processing. A continuous improvement cycle is being driven by various researchers and various hardware companies. Hence, it leads to quantum enhanced learning algorithms. There are a couple of challenges. Like noise, decoherence, and hardware limitations. These are being addressed. Various initiatives and research projects are going on. However, these things are also serving as a limiting factor for adoption right now. Let us hope that we hear positive news about these challenges. Next one. So what is the motivation factor? Motivated by access to cloud-based processes and commercial applications, we are able to access and have a hands-on to QML very easily. It is developed by noisy intermediate scale quantum disk devices, wherein there are very few qubits, it's noisy and it has got low grade fidelity. QML applications are triggered due to Xanadu's PennyLane and TensorFlow. Popularly, these are the two frameworks devices which are triggering adoption of QML. These are the popular frameworks. Hybrid frameworks are available to leverage the benefit of classical and quantum computing, but that has got variational quantum circuits. Let's look at the next one. So the process flow remains same between the classical and quantum computing. The training data which is used to build the model varies. The testing data is used for the application. Classical data needs to be reformed to suit the quantum machine. The measurement step in adding the estimate to the outcome of QML algorithm is something which is the essence to the success. However, the outcome of the QML, sir, we are not looking at the slide. If you can just move back to the slideshow, please.
Yeah, one second. Okay. And then I will go with it. One second. Probably it got flicked. One second. Yeah, you are in this one, right?
Yeah. So outcome of the QML algorithm needs to be reformed to produce the results. So this is where these results are to be used and interpreted in again in classical domain. Next slide, please. So here is a quantum pipeline. In a quantum machine, we have got an input, process, and output. On the left side, we've got various types of inputs that initializes various processes. Once processed, it gets a interpreted output or prediction or probabilistic result. So this is how we build quantum pipeline. I'm a sales guy, so used to sales pipeline, but I thought let me bring in a quantum pipeline kind of phrase in this discussion. Next slide, please. So with this, thank you so much, and I would like to hand it over to Prakash to take it ahead. Thank you so much for your time and attention.
Thank you, Chintan, for the basic concept you have brought in. What I will do is I'll just compare, because this is a little bit of a high level at the quantum, because you need to understand quantum machine learning part. A lot of people know, but in the quantum we have got representation of information. In classical we use bit 0 or 1 for voltage level, whereas the representation here is actually a vector, and the vector is they use bracket notation. So the probability is that you have a 0 or a 1 based on the qubit, which is based on, it can be simultaneously 0 as well as 1. And how do you know? Because this is based on the superposition, so it is state based. So state can be spin up or spin down, because this is subatomic particle which are represented in quantum. And so you can say it's a kit 0 plus b kit 1, which is the qubit, and square root of a and plus square root of b together is equal to 1. So probability is 1. So basically you are saying that it can be based on superposition of the states. So it is state based. In the case of classical, we have 0, 1, and then we form the registers. Here you have got probability that it is 0, it's 1, and then you can represent them as a state, as a vector, and this is in the Hilbert space they call it, which is a vector space. So and this is vector space, and it can be n dimension, so you can have as many qubits you want. But the advantage of this is you will get at the bottom, you can see information size. We have n state, but one at a time, right? But so here you have 2 raised to n. So if you have 5 or 4 bits, let's say, and we are using 4 qubits, then 2 to the power 4, 16. So you will have 16 states in the case of qubits. So qubits are nothing but subatomic particle which are manipulated or which can be applied to create gates. There is a gates which is different logic gates on the and are the normal classical gates, and they follow the Boolean algebra principle, whereas in the case of quantum they use superposition, entanglement, and interference as the properties of the qubit, and they are reversible, like you have Fourier transform, inverse Fourier transform. So the transforms are, but in the case of a gate, if you take and or, if you have 0, 0, output may be 0 or 1, and so reversibility is not there. You can check that out. And talk about robustness, this classical computer are robust, and they can operate at even at 400 degree Kelvin, which is nothing but 273 plus whatever you want to say. That is, but in the case of quantum computing, they work, they are sensitive to noise, as Chintan mentioned. They need to overcome whatever the system and the environment, thermal noise, etc. So therefore they are operated at low temperature. Currently the superconducting quantum, which is the based on what you call trapped ion, which is based on the what you call the junction, which is Josephson junction, and operated with couplers and all that. So those are electronics hardware stuff. Whereas in the case of hardware in classical computing, we use the LSI, VLSI, and all that, logic gates and all that. In this case, the poly X, poly Y, poly Z, which is the standard gates we call it, and then you have got various other like Hadamard, and so many gates are there. Those gates operate on the analog domain, and they are able to use charge tunneling and various cavities and microwave couplers, etc. So that's a hardware portion of it. So quantum is a bit different and therefore not directly applicable as we use classical computing with the confidence. And that is why there is a NISQ era, we call it, because we are not able to generate sufficient qubits. Plus, to do the fault tolerance, we need thousands of them to reduce the error. So that's the key. So we talk about basic quantum models before I move on further. So basic quantum model, the first quantum model which was proved to be deterministic. Of course, they are indeterminate, but in the case of if you have a function with 0 and 1 as the set, and if you have, that is the quantum states, and if you have n of them, and then if you want the results to be either a 0 or a 1, that's doable by using the gates. So the gates, so example, if I have a, in this case, let's say we have 4 qubits in the top. In the diagram, if you see here, 4 qubits, this is a gate, Hadamard gate. So if you have 4 qubits, then normally for us to compute that, we may take 4 operations one after the other. But in this case, doing a Z basis, they call it as Hadamard does what you call the, it is able to combine in a Z basis, and you are able to get what you call the you are able to combine the signals and be able to get a single signal, and that signal, when you apply with transforms, you are able to get a circuit, a unitary circuit. Generally, all quantum circuits are unitary in the sense that they are reversible and they are they are optimized. So if you think of a circle, and if your circle is having a unity and the vector is represented by the arrow from origin to the circle, you keep rotating it. So vectors are transformed basically, and most of them remain one, that is, they are unity. But at the same time, what happens by doing this is you are able to get a vector transformation. So the change in the phase is what determines the position, and therefore by having a, this is called, the circuit is called as oracle or sometimes even ansatz. And so all these circuits which are there, they are able to combine together, and one shot you will get an answer. Whether the this operation is either you have functions for 2 of them being ones and 2 of them being zeros as an output, but that you do with 4 operation. Here you can, with single operation, if you initialize, you will be able to knock out and get the output, and therefore this is faster and this is deterministic. So that's how because we are encoding, right, we are taking that every binary bit is equal to 1, like 0 0 0 1 0 1 0 0 0 0 1 0 and 1 0 0 0. So those combination we have sorted out into 4 operation, whereas here with a single operation, ket 1, the spin up, spin down. So spin up is 0, ket 0, spin down is ket 1, and then you can have a column matrix associated with it. You are able to resolve by combining, by superposition of the inputs and get the output, and you can measure the output. So Deutsch-Hauser model is the first model which proved that you can do quantum inputs by encoding and then applying the applying them to the inputs of the gates and producing the output. So this is the quantum model. Now there are many more, but I will just point to Shor's algorithm as one, because here what we do is you have a number of initialize. You initialize to ground state. So they are called ground state and the energy state. So you have n ground states, and then you are applying the Hadamard gate to make them combine with each other, and obviously it is equivalent to a vector basically. So you can say they are all vectors, and these vectors in the vector space are Hilbert space, they call it. which is a vector space, and where you are going to transform and apply the QFT based on some formulation. I will give you the formulation, but essentially important thing is you are going to change the phase. So whatever bits are kit 0 or whatever spin-ups are there, all of them will be combined with the universal gate to be able to do a C0, they call it. There are many gates. So explanation wise, I will just say that you are able to get the phase changes, and the phase changes can means quantum phase estimates. So you are able to get an estimate of phase for each of them and then combine them together as a inverse Fourier transform and then get the measurement, which is analog measurement. So there is a whole slew of things. I will skip this, but the idea is Shor's algorithm leverages the quantum Fourier transform to efficiently factor large numbers. So large numbers can n, and then you take a GCD of some n is greater than a is greater than 1 and n is the one which you are trying to do the identify the factors, the prime factors, and then you can estimate by phase angle. You are changing the phase in the inputs. So they are called, some of them, these are called ancillary, and the actual ones are the one which are applied, and then you get the result. So ultimately there is a classical to quantum, and then it's a subroutine. Usually QFT and QP are quantum phase estimation, and quantum Fourier transform takes the classical input as encoded and then applies the quantum, and then comes back again, applies the measuring in the analog domain. So that is why these are complex to say that there is no standard like saying this is classical and this is quantum. It can be classical, quantum, classical, or quantum, classical, quantum. So these are hybrid. So even though Shor's algorithm itself is quantum based, but it also needs classical implementation on the pre and the post to determine, and that is the details are in the heavy. I will just leave it at this time. So you also have SVM, and that is classical and then quantum, and same way neural network, classical and quantum based. So this I will leave it because this Gokhale is going to cover. The only thing I would say is if you have a quantum pipeline, you have the qubits, which are kit 0 or kit 1, which is nothing but a bracket notation, we call it. So which is the Amazon bracket, or even IBM and Google and all of the players, key players, use the bracket notation established in 1928, and that is what is used to feed, and everything is unitary basically. That means everything is normalized to 1, and it's a vector, and it is rotating in the what you call the n dimension, depending on the Hilbert space which you are working, which is a vector Hilbert space. And then you apply the model. You can take any of the they call it as either oracle, or they call it as ansatz, and so you can apply the gates, unitary gate followed by any of the model which is in terms of circuits, and you can measure at the end of it. So this is QML pipeline. And you similarly you can extract the output, get the output, and again convert similar way. Example here you can see the measurement which is there, that is analog measurement, and it's a probability distribution. So probability density, probability mass distribution. So discrete, these are discrete, not analog. In analog sense, you do a probability is more, it is discrete. Here analog is continuous. So here we take a discrete value because we want the distribution to be able to measure and be able to provide the output essentially to be able to measurable. Now example of a parameterized circuit, because the circuit when we saw, this is you have a Hadamard gate, you have a RY and RX. RY, RX are nothing but you rotate around the, if I take a circle with a arrow pointing as vector, and if you are doing a Y basis, X basis, Z basis, there are three: poly X, poly Y, poly Z. Poly Z is the standard, and that helps bringing the qubits and then be able to mix them together to get a output, and which you can apply the XYZ basis. So example, here you have parameter input and parameter weight, and you can see Qiskit circuit import parameter, Qiskit import quantum circuit, and these are available, and I think I'll leave it to Gokhale to present it in a detailed manner. But parameterized circuit is the important thing, and those circuits are used to get the output. And here I go into the what you call the QML algorithms. There are many algorithms. There are, because of the technology at the hardware level or at the analog level, you have quantum annealing. There are two gates based. One is two bases for what you call so E equal to mc square. We know, everybody, that energy is mass, and to c square of c, we just did. So energy and mass are interchangeable, and that is why the physics of is based on the quantum mechanics, and that is basically saying that you can have a particle converted to energy. So photon example. So you can have electron being the particle with some mass, photon with no mass, and that has got energy, which is wave energy. So you can convert between these two. And the annealing is a process where you are more worried about the volume and the energy level shift, which occurs by having these molecular level like electron, proton, etc. And it can be atom, it can be neutral atom, whatever. Based on the energy level changes when they move from one to another, you can apply. This is slow moving, and therefore steady state, based on the whatever your Carnot and other cycle theorems and all that. In the annealing is a process whereby you are able to change the state and of energy slowly and steadily without abrupt changes, and that's why the annealing does not require, can be represented by shallow circuits, we call it. So that's why annealing is the most used currently. You can use other models also for the algorithm. Models and algorithm we treat as interchangeable, in the sense that you have a hypothesis that this is what is the null hypothesis, and then you try to prove it or disprove it, in as in data sciences. Similar thing, it is a model. You give the input, you transform and get the output. So quantum enhanced reinforcement learning, search algorithm, this is k nearest neighbor. Also there is a what you call Grover's algorithm available. All are, these are based on linear algebra simulation. So 1, 2, 3, 4, you can see this. Then neural networks, hidden Markov. When you don't change the state, or you only consider a state within a given time, then it is Markov model usually. You don't look at the past and the future, just take what is in this given state. And then you got the pattern matching and classification and sampling techniques and all. So many algorithms are available for QML. This is not the only the exhaustive list, maybe much more. Like if you go by use cases, then it will be much more different, but at this time this is enough. So encoding, so few things about encoding. If you are going to do any processing on quantum, and if you have a classical data, you have to encode it. Now how do you encode it? As I said, if I have 4 bits as 00011011, I can put it as a ket 00, ket 01, ket 10, ket 11. So that is like you are taking 2 qubits and representing them as qubit one system, which is on the first digit, second system which is on second digit. You are combining them as a ket 0, ket 1. So if you have a pure state, then there is no entanglement. You can combine them, but there is no entanglement. If you have 2 qubits, then 2 qubit systems, you do have some basic level of entanglement, and they are called Bell state, and they are popularly used. So encoding can be simply take the binary and then convert it, represent them as like if I have 3 qubits, then 000001 up to 111. So I can say those are the 7 or 8 states, 0 to 111. So you can encode them direct binary. It's called direct encoding. So you can do direct encoding. You can do like we do in the hash tables. You convert, apply some formula, and then you are making sure. But hash table has a many to one also possible, or one to many is possible. So that's the problem we have in the hashing. But we can encode based on how we want to encode. There are different algorithms, like example here, cat 101. So you may have sevens, we can have cat 1. This always means it's a tensor product. All quantum vectors, they do tensor processing, and therefore all tensor processing vectors are represented in the Hilbert space. So example, you have a hello, ASCII of H, ASCII of E, ASCII of L, ASCII of L, and ASCII of O. These are taken as encoding mechanism. So hello can be encoded not direct, but rather using a ASCII code as a converter, and then we can reverse back later. So we can encode in different ways. So there are superposition encoding. So Hadamard get, when you apply it, always does a superposition, and so you can see here you can do a superposition 101. So examples of various encoding. So you have 101. Of course, I think this is a little bit not sure this is correct, but you can have 100, 001, and then 000. Maybe this I have to verify. Google, I'll need to verify. I think this was a mistake. 78, 7 ASCII and 8 ASCII. You are saying only 2 states you are representing, and therefore 1 by root 2. So always you will have, if you have three qubits, then you will be 1 by root 3. If it is 5 qubits, there will be 1 by root 5. So your encoding is superposition encoding represented by linear combination. Normally we try to keep linear, but nonlinear encoding is also popular for cryptography, etc. So I will just say that there is angle encoding, rotation amplitude encoding, and then there is a what you call the rotational encoding, which is z basis, which is the most normal, and then x and y basis. So z, x are the two popular one. So if you have x basis, you apply Hadamard, you can get z. You can, so the interconversion is possible. Basis representation is very important. So standard basis is always z basis, and that is poly z we call it, and you can use it in terms of either you represent in terms of angle, or you represent in terms of trigonometry, like cos square plus sin square, beta plus cos square, beta is equal to 1, and that types of, except the phase being different, you can see that Rx, which is there, it is e raised to I theta x by 2. If it is y, then it will be I raised to I theta y by 2, etc., etc. So these are matrix representation, 0 minus I, or 1 minus I 0, and that depends on the angle. So whether you rotate about x-axis or rotate about y-axis, you have different matrix representation. All qubits are represented by ket is represented by column, and bra, which is the reverse pointing bracket notation, that is taken as what do you call the row vector. So you have column vector and row vector, and you know that when you do a transpose, you need to properly multiply to be able to do all the matrix operation. So encoding methods, there are many. One of them is angular, using Rx, theta 1, theta 2, theta 3. 3 angles are taken. You can have different way of encoding, either amplitude encoding or angle encoding. All this comes to the summation I equal to 1 to n of whatever. In this case, we have taken ket 0. It can be ket 1. It can be bra 1 or bra 0 or whatever. So these are the notations here. So example, encoding 16 features if you want to. So features are encoded. So that is why it is called sometimes parameter encoding, quantum parameter quantum encoding, or PQC, but not the cryptography. Okay, so encoding here, example, if you have 16 features, you can encode 1 to 8 feature using Rx. That's what it is represented, and you can see this is a block sphere, is a representation of z basis. So you take the angle from z, theta 1, theta 2, and whatever, and then based on the application of the transform, you can see initialization is 0, and then you got Q1 to Q8. In same way, you got another bunch which is based on Ry, not Rx. So you can have features 1 to 8 represented by X, 8 to 16, 8 to 15 represented. So 0 to 8, 1 to 8, and 8 to 9 to 16. So this is kind of a representation. And the other way is you can use the column vector, as I mentioned, column matrix, which is representation of X. And then this is the probability that it is 0.88 spin up, and probability it is this one represented. So 2 qubits you can represent by applying the Hadamard for superposition, and then apply the Rx and RZ in this case. The other one is RZ. So you can apply different encoding method. It's all encoding and then decoding. So I hope encoding methods, there are many. The quantum state is always written ket psi equal to alpha ket 0 plus beta 1, beta ket 1, and square root of alpha square plus beta square is equal to 1. That's the standard representation. The encoding values in this case are given, and you can do a ket x, the psi of x, which is the x, and then you have got the x. So these are the formulas you can just apply, and you can normalize them so that they are in the unity space of vector representation. And encoding methods are humongous. I'll just leave it. QRAM I'll skip. This is, I think we need to go to the Qiskit. Qiskit is the one which is used earlier. Now with this I think I should hand over to Gokhale. Gokhale, welcome. Take over from here. I have tried explaining encoding, decoding, and whatever QML, whatever the. Go ahead.
Thank you, Prakash, and thank you once again the entire panel and the QIT working group for giving me this opportunity to be with you all. This would be something like a 101 session on quantum machine learning, a quick overview of a few of the algorithms. The idea is not to go deep dive into the algorithms, but just to get an appreciative type of idea about what these algorithms are all about. Am I audible, Prakash? All clear?
Yeah. Go ahead. Yeah, everything is fine.
So fine. So I have a small issue a little later on, because I thought probably I can also show my screen where I've got a collab. If that is possible, a little later on.
I have the collab. I have the collab which you mentioned.
Okay, fine. Then fine. No, not right now. Not right. Okay. Thank you so much. So can I go to the next slide?
Yes.
Yeah, we are going to probably focus our attention on PennyLane. PennyLane happens to be one of the sought after, let's say I should say, platform for developing QML applications. And next slide, please. And why PennyLane? Essentially, PennyLane is a cross-platform Python library, and which also means the fact that you can use a import of PennyLane library or the PennyLane modules, and then write standard Python code, and then still set up your QML algorithm. And that particular QML algorithm will have a slightly different structure. Even though it is all composed out of Python statements, it will have a slightly different structure. And how does PennyLane look upon your entire, let's say, QML application, or even a quantum application, I should say? So it starts off with defining what are called as quantum circuits. Right? The circuits are made up of a bunch of these gates, like the Hadamard gates and some rotational gates, and maybe you have about C0 and CC0 type of gates. All of that bring together, you create a quantum circuit. And this quantum circuit is identified as one unit of a computation, something like a function. And these are called as quantum nodes. And the best part about this is you also give some additional properties to these quantum nodes. You specify where the quantum node is going to execute. Right? So it's something like you are assigning a small runtime information also to that. So you identify what is the device on which this particular function would execute. So that is the reason why probably you can delegate, saying the fact that this particular function would execute on node A, or maybe device A, some other function will execute on device B, and so on and so forth. And that is one of the reasons why it gives you an opportunity for you to set up your applications and algorithms to work on various backends. And it's a simple, normal Python library which has got a flavor towards machine learning. So it's very much like you have got, let's say, scikit-learn supporting classical machine learning. Here you have got a bunch of constructs which allow you to define your QML type of workloads. And one of the reasons why this has also become popular is it can handshake very well with other ML frameworks. Like it can handshake with the NumPy, and it can also handshake with JAX. This has come out from Google, and high performance compute environment. It can also handshake with PyTorch. A lot of deep learning algorithms are implemented extremely well in PyTorch and TensorFlow. And the best part is PennyLane can typically gel with all of these frameworks. Next slide, please. So here is a small example of how a quantum circuit is going to be defined. It's like a small Python function. You just import PennyLane as QML. Obviously, you need to pip install PennyLane before you set up. And then after that, you just define your own circuit. And the best part is these circuits are all parameterized circuits. Okay, so here, if at all you talk about, let's say, 2 qubits and you set up a circuit over these 2 qubits, the notation that is used out over here is called as a wire. Because wire is where you actually wire up and rig up your circuits. So you define what goes onto the wire number 0, what goes onto wire number 1, how are both these two interconnected, probably using a CNOT gate. And finally, you are just also identifying what is the return value. This return value is something like you're taking a measurement, and the measurement is on the poly-Z, and that measurement is something which you are going to extract. So it's something like that. Next slide, please. Okay, and so as I told you, this quantum function is the one which you can identify with a bunch of parameters, and these parameters can accept normal classical inputs and also allow it to operate on the quantum operators. Now, these particular quantum operators are your Hadamard gate, the rotation gates, your C naught, and whatever gates you typically put, the Toffoli gate or whatever. All of those gates typically happen to be made available to you, and you have a bunch of templates. And the best part of the template is something very much similar to, let's say, a small library. You have got a scikit library, and that scikit library has got a templated way by which you can typically call in a function to carry out a task. On similar lines, you have got templates here to carry out some tasks in the quantum realm. So that is what it is. And as a normal programming language feature, it also supports all your control flow structures like for loops and if statements, and you just name it. All of that will be made available. The way it identifies definition of quantum values is in the context of referring to from a qubit register. Right, so normally it's something you can treat this as a vector of quantum values, as simple as that. So it's like a vector of quantum values, and that is what a qubit register maps into. And then you can carry out a whole bunch of operations on that. And at the end, you perform what we call it as a measurement. And measurement would be typically yielding a specific value that would be in a you can just map it back into a probabilistic frame, and then determine the exact output could be either a 0 or a 1. So at the moment we do a measurement, the quantum circuits collapse to either a 0 or a 1. Next slide, Prakash. So when you talk about devices, remember we spoke about the circuit and the devices, both of them bundled together. And the device is essentially where the algorithm or the code actually runs. Right, so we normally talk about a device, and the device is supposed to be an instance that I derive out of a device class. And here is a small example of setting up a device, and this particular device is a default qubit. And I say that this particular device is going to operate over 2 qubits or using 2 separate wires. So this device is going to be initiated. It's something like, it is a constructor for that particular device object. And once you have done that, you typically set up a default environment for that. It could be mapped into a local simulator. It could be mapped into probably a little later on into an air simulator or whatever. Or it could be mapped onto a direct quantum machine for which you have an access. Okay, so PennyLane gives you a bunch of these sort of devices like default .qubit is something which is very popular. Lightning.qubit is something which is offered by even Google, and it's supposed to be a high-speed simulated environment and so on and so forth. Okay, so any other device, if at all you have in mind, that can be also installed as a device level plugin. Next slide, Prakash. So what I mean to say is, PennyLane, I'm not trying to sell PennyLane, but I'm just trying to impress upon the fact that PennyLane gives you a very good opportunity to get started with working in QML domain. And finally, what you're going to do is what? You're going to bundle both these two. Your quantum task in the form of a function and your device related information. You bundle them together and then you create what is called as a execution context, a Q node or quantum. Right, so quantum node is what we are going to define, and quantum node is what we are going to trigger for run times. Next slide, please. Okay, so you also have got a very nice, let's say, a construct that is available through which you can even visualize your circuits. And thanks to Matplotlib gives you also a very nice way by which you can come up with a pictorial representation of whatever circuit you set it up through PennyLane. So PennyLane also talks very well with Matplotlib. Go ahead, Prakash. Next slide. So here is a small sample code, how it looks like. I'm not getting into the deep dive of this particular code, but structurally look at that. You're going to import a PennyLane and then typically call it as QML, and that is a alias which you give for PennyLane. And then you also have from PennyLane imported NumPy as NP, and then you can create a device. So this is a device which you have created. Here is a device which is set up only over a single wire, and then you define what exactly is a circuit. Right? So maybe you're performing some rotation about the X, you're performing a rotation about the Y, and then you're collapsing that to a measurement around poly Z. And this is the definition of a circuit, and then you have mapped it onto a Q node. Right? So basically, this Q node is defined over the device one which is created. So this is how you set up your association between the circuit and the device to work on. And if in case you would like to work on this and then estimate some cost, right? Normally we talk, whenever you have machine learning algorithm, we typically talk in terms of the cost function, try to minimize the cost function and check out what exactly is the variation in the cost function. And then, the gradient descent algorithm typically gets applied out there. All of that is very much quite a similar line. Okay, next slide, please. So the code does not really look very strange. The other thing about PennyLane, why it's that very important, is that it integrates very easily with Qiskit. Okay, so you have got PennyLane Qiskit as a plugin, and typically it now allows you to access Qiskit resources. Like Qiskit also gives you an access to a QML device like Air as a simulator, or probably you can also just access it, the physical hardware, provided you have an access to that with an authorization and account and stuff like that. Okay, so it also handshakes very well with the hardware units, or probably a bunch of simulators as well. Air simulator is something which is very popular in the context of IBM's Qiskit. PennyLane can very easily talk to that. Next slide, please. So here is a small example. Now, PennyLane offers you a whole bunch of templates. Now, these templates are what are called as ansatz. What is an ansat? Ansat is something like a ready-made, pre-constructed circuit that is given to you, which can be parameterized. And they have got a whole variety of about, I think, 22, 23 plus ansats which are there. And depending upon what you want, you can pick them up. And then, use the parameters to redefine the structure, redefine the actual parametric information regarding to that. So here is a small example of how the ansatz looks like. We have taken, let's say, the Titanic data set. It's a very popular data set. And out of that, we are only considering, let's say, only these 4 parameters over which we would like to build, let us say, some model. Right? Because it is 4 parameters, I just pick up this sort of an ansatz. This ansatz typically does what? It does some rotations about the Z and the Y, and the Z and the Y. And then, this is typically where your entire algorithm gets implemented here. right? So we are going to look at that a little later on. We will just see the fact that this is a structure given to us as an ansatz, and then all I need to do is what, start off with some rotational angles, and my so-called entire algorithm of machine learning in the quantum realm boils down to trying to find out how to modify these rotation angles. Right? In the case of your classical neural networks and implementations, what you do is, as part of the learning, is you try to realign the weights. Right? Quite similar to that, here you get back and then you try to realign these rotation angles, and in such a manner that the overall error, overall cost function, whatever you define, the cost function is minimum. And that is basically the complete idea behind setting up a quantum-based machine learning environment. Okay, so you use these ansatz, and the best part is PennyLane offers you a whole bunch of answers. You don't have to start everything from scratch. You take this template and then get started, and then put up your comprehensive pipeline, and then you are ready to go. Next slide, Prakash. So very quickly, let us visit a few of these cases. Prakash, do I have another 10 minutes, 10 to 12 minutes?
Yeah, you have 10 minutes.
Oh,
10 minutes,
so
but try to put up in 10 minutes.
Yeah, I'll try to finish it off. Yeah.
Yeah.
So when you talk about quantum neural networks, we understand the fact that these are primarily built using fundamental building blocks which are variational in nature. So we build circuits which are variational. And what do you mean by variational circuits? These circuits are parameterized. Like, for example, I get a block, and that particular block would have, let's say, 3 gates, rotational gates, and then I've got initial parameters wherein I say that the angles are typically at maybe 0, 0, 0, whatever, and then I offer alternate to that. I just change these particular angles by, let's say, pi by 6, pi by 4, pi by 3, and that will give me a second state after I perform some operation. So these are basically epochs which I go on and are iterative type of cycles. And ultimately my objective is to see that by managing and manipulating these theta values, the rotational angles, and I'm trying to converge down to a minimum form of the so-called cost function. Okay, so that is exactly what we are planning to implement in a variational quantum circuit, and variational quantum circuits are also identified through PQCs. Okay, parameterized quantum circuits. Next slide, please. So this is the fundamental thing. So how do we get started with? First and foremost thing, right? You have an initial vector of the values, and all of them are typically initialized to get zeros. And then you have a encoder, right? This particular encoder typically could be a comprehensive rotational operations, and that's how you use encoding techniques. And those rotational encoding techniques which you use out over here invariably become the so-called pre-processing activities. And that is the best part. So you save a considerable amount of computational cost and time by encoding itself. So the moment you are putting up some effort in encoding, you already have something that is ready, which can typically participate into some sort of a set of linear operations. Next slide. Then you actually bring in the parameterized operations, right? Each of these parameterized operations is defined over some parameters like theta 1, theta 2, etc. And normally what we do is we'll have a series of them. Right? Not necessarily 1, 2, but you'll have a series of them, very much like the way we do it in a deep learning model, right? So we have got a series of transformations operations which are there even before you actually finally get down to the neural net, the last component out there. So similarly here you have got a whole series of parameterized operations, and all I'm going to do is that all these parameters are going to be modified in each and every epoch. Now the thing which you need to understand is something like this. In a normal classical neural network, what we normally have is you have got typically an activation function. The activation function is a non-linear operation. Now, how do I have a non-linear operation out over here? Most of the operations are linear, right? So what is typically done is something like this. As of now, there are some people who are probably trying to implement system mechanics wherein a quantum circuit itself exhibits some sort of a non-linear behavior, something like a sigmoid or a ReLU. They're implementing that, and they're saying that, okay, we are going to now use this as a activation unit, right? But the best part is something like this. whenever you do any of these core basic transformations, which are unitary, all these transformations are linear and they happen in the so-called Hilbert space. We know about that. But the moment I do a measurement, what will happen? We are taking this and then trying to project it into another space. That's the concept of a measurement. And this process itself is non-linear. So what I can say is something like this. Why do you have to really worry about doing that so-called defining your activation function in a non-linear space? We can do that at the time of measurement. So measurement itself is automatically going to give you that fundamental advantage of implementing a activation function. So now you have got double advantage. One, you have got linear transformations, which work pretty very fine. You can parameterize them. Second advantage is both the encoding gives you that opportunity to transform your data and then make them also available for pre-processed state. And then you also have got a measurement that will also act as the so-called mechanism for implementing the ReLU function or activation function. Right, so that is how you gain a lot in terms of implementing a neural network in the quantum domain. Next slide, please. So ultimately, you put up your measurements, and then the measurements outcome you take it and then put it into a classical system. And what you do with the measurement? Go next slide, please. So one slide previous, sorry. See, for example, out over here in the intermediate state, you'll have a whole series of weighted matrices, right? I'm just putting them as weighted matrices because all these are a whole bunch of circuits which are normally the identical circuits which repeat. And each one of them have their own parameters. The parameters are different. And I can just combine all of them into an equivalent W matrix. Right? So that is what I'm showing in the next slide. Next slide, Prakash. So this is your equivalent W matrix, which can list out a whole series of combined operations. And remember, all of them are linear. So that is the reason I can just come up with an equivalent W matrix. Next slide, Prakash. So this is what I was talking to you about the ansatz model. I have got a whole bunch of ansatz which are there. You can pick up as per your requirement and then use it in your implementation. Next slide, Prakash. This is a slide about how to select your ansatz. Plenty of them are available. So what exactly are the way by which you're going to get started with? Okay, so experience will typically tell you how to go about doing that. But there are some ansatz which are probably recommended for a specific type of a problem. Right? There are some ansatz which are more specifically tailored towards using the entire hardware in a more effective manner, especially in the NISQ type of era of computation. Then there are some ansatz which are highly parameterized, right? So you typically try to probably pick them up. All ansatz are parameterized, but there are some ansatz which are extremely highly parameterized in terms of using what they call it as a tunable gate. So you try to pick them up. So there are several ways by which you typically land up selecting an ansatz. Next slide, Prakash. So when you talk about a variational model, remember your neural network is based out on ansatz, and that particular ansatz is made up of, let's say, your variational models. And this will use what are called as parameterized variational circuits, right? And what exactly are they? Whenever you talk about the neural network implementation, three things have to be brought into picture. One, the ansatz. Then you have to also define a cost function. Right? The cost function typically tells you whether are you progressing down towards the optimal solution or not. And then you'll have an optimizer, very much like a conventional system, right? You typically look at the error, and that particular error is getting identified as to how much of the weight you are going to change. So what exactly is the delta changes to the weights, and then you push it back into the backprop algorithm. So something quite similarly, you've got an optimizer also. And out over here, if you look at it, this cost function estimation and optimizer normally would be outside of the quantum. And here we talk about a hybrid implementation. Right? So you're not having a pure quantum implementation. You're going to have a quantum implementation to speed up all the computations. And these computations now would be carried out in parallel. Now, for example, in neural network, layer across layer, all these calculations can be computed exactly in parallel. In one single shot, you can just complete that. But the moment it comes down to the output, ultimately you'll have to get back and then get started with the data, then you estimate what exactly will be the modification I need to do, what exactly is the error, what is the gradient, you have to estimate all of that and then come back into maybe your gradient descent algorithm or something like that. So here is a small example of a PVM. The PVM typically starts off with an encode mechanism, and there's a variational part. Here is where you typically define what should be the values for your angles. And these are all entangled with each other, a complete comprehensive entanglement. And this entanglement is what is realized using C-NOT gate. And then you have, once again, a second level of a rotation. So you have essentially 8 parameters, which are rotational values. And your idea is to optimize what should be the perfect value of this combination of theta 1 to theta 8. And this can be done typically not in sequential order, but they will be done in parallel. So this becomes one unit, and you keep on repeating that in multiples of whatever you want, that is called as a parameter P. So here is the second one, the third one, the fourth one. You can just keep on doing that into multiple layers. So this is what is called as an n times variational structure, which you're going to implement. Go Prakash, ahead. So finally, this is what is your W theta. Whatever we spoke just now is all your W theta, and then you start measurement. And another best part is, when you talk about measurement, the moment you talk about measuring one output, the entire circuit collapses. So the big point is, why do you want to really measure everything? I can typically measure one and then probably get the outcomes and then solve it across through a probabilistic distribution mechanism. So that is typically what people also tend to do. Rather than measuring all of them, we just probably get started with only measuring one, and that is good enough for me to estimate whether the output will be in a state 0 or state 1. Next slide, Prakash. When you come down to optimization, I think we all know this is typically the gradient descent mechanism. And gradient descent mechanism, once again, is in context of a cost function which you define. And this is a classical approach. And this classical approach is still there. So optimization in the context of a quantum neural network still happens to be in a classical way. So it is a hybrid approach. That is what is actually considered. Next slide, Prakash. So this is a big picture for what we call it as a variational model, and this is with feedback. So how does it work? You have the inputs, then you typically have the so-called feature map, then you have got the variational circuit, right? This feature map is basically the so-called features vectors which are getting encoded. Then you have got the variational circuit, and then you have a measurement. And the moment you have got the measurements, you just take the outputs and then give it to a optimizer function. And this optimizer function typically works in the classical space, and this will typically tell you the way to update your theta values, which you back propagate and then try to make adjustments to both the rotational values here and the variational circuits here, and this particular thing goes on and on and on. Okay, next slide, Prakash. So how do you handle this QNN with PennyLane? I'm just giving you a small flow. You start off with the first step as choosing a device. Then you go down to defining your quantum circuit, or more specifically, the complete quantum node. Remember, quantum node contains both the quantum circuit as well as the device. That binding is there. Then you identify what are all the trainable parameters which you really require to handle. That is informed down to PennyLane. And then you normally integrate that with some ML framework, right? Maybe it could be using Torch or could be Keras or whatever. So have that construct which allows the entire Q node to be wrapped up into either a Torch or a Keras layer. Next slide, please. Step number 5 is where you build your hybrid model. Remember, this is not a completely a quantum model. It's a mixture of quantum layer as well as the classical layer. Classical layers are built in PyTorch or TensorFlow, and then you have got the quantum layer that is available to you through a wrapper built over PennyLane. Then you define your loss function. You define what exactly will be your optimizer, and then you typically do all that estimates for MSE and stuff like that. And you go ahead with the training, the model. Training is once again absolutely quite the same. Like you typically take your data, split it up into train and test components, go through the training over the training data, pick up the testing data, do a validation, check out the accuracies. The remaining model is absolutely the same thing. We are not going to change that particular part. Yes.
Okay,
So
do you want to
yeah,
speed up on QC?
yeah,
Yeah.
I'll just very quickly I'll just go through that. So the bottom line is this. Whenever you talk about any quantum machine learning use case for an implementation, you talk about support vector machine, or typically you talk about random forest, right? All of these now you have got a sort of an implementation through QML. So which part of this algorithm are you going to really address first? So most of these algorithms have something which is compute intense. Now, for example, if you take the SVM, in SVM, to find out sort of distances, distances calculations have to be typically done. So what is the distance calculation? You typically talk about trying to identify the midway of the path, and then you are going to identify how many of these particular points lie on the left side or onto the right hand side. And that is typically estimating this inequality. W into x minus b, whether it is less than 1, equal to 1, greater than 1, or equal to 0, negative or positive. Now, that estimate is something that you need to make for a whole bunch of data points. And just imagine if at all you have got hundreds and thousands of data points, that becomes compute intensive. And this is for one specific case of a W and a B. And that you are going to typically try out multiple such ones. That is one issue. The second issue is, next slide, Prakash. What might happen? Go ahead, next slide. Next slide after this. What might also happen is something like this. Support vector machines typically handle cases very well if the entire search space is linearly separable. What happens if the search space is non-linear, not linearly separable? In that particular case, we typically use a kernel which acts as a transformer, and that will try to project your data points into a higher dimension space. And we try to identify a suitable transformer so that the higher dimension space itself is somewhere separable through something what we call it as a decision surface, and that decision surface is also called as a hyperplane. Right, so we need to identify the hyperplane, and we also need to identify the so-called higher order kernel, and these are once again complex operations. So you're doing a transformation of your input data. Now this once again rings a few bells. What I mean by that? When you have your input, the way you encode itself is one opportunity for, applying a small kernel. This is what is also called as a kernel trick. And that particular kernel will also do two things. It will not only encode, but at the same time, it will also transform it into a higher dimensional space. So you are typically once again hitting two things at one single operation. And that is one of the reasons why we say that, okay, you see some good opportunity to apply quantum algorithms for even support vector machines. Next slide, Prakash. These are all the whole bunch of kernels. Next slide. Let me quickly wrap this up. Next slide. Okay, so what we typically try to do is, the kernel, whatever is there, what that kernel is used is the kernel will now take your input data. It will not only encode, but it will also do a transformation into some sort of a hyperplane. So it is typically doing that, and then that also can be parameterized. That's the best part. So a kernel itself is available to you as a VQC, and that is one wonderful advantage. So when you talk about the hybrid approaches, maybe the hybrid approaches could be coming through a neural network or coming through, let us say, your SVM, support vector machine. You have other ways by which you can think about optimizing your, let's say, an application, optimizing your solution. And for that, we have just now seen VQCs, which typically very good for implementing ML models. If at all you have got some sort of a algorithm or a problem which is purely in the higher order computational planes, or it's purely an optimization type of a plane, how do you handle that? So you have got what are called as QAOA algorithms. So these are called as quantum approximate optimization algorithms. I have a few slides, 1 or 2 slides. I'll very quickly go through that. Next slide, Prakash. Yeah. What QAOA does is something like this. It typically defines two working entities for us. Okay. So these two working entities always work together in a pair. Okay, so what we'll have is something like this. It is one single circuit, but it'll have two layers. One, we call it as a problem Hamiltonian. I'm not getting into the details of that, but that actually does the core of the computation, followed by what is called as a mixing Hamiltonian. That guy will add a small drift into the information. Maybe let's say the core one is just setting up a bunch of let's say angles, theta 1, theta 2 to theta 3. Mixing Hamiltonian will just identify small delta theta working on top of that. So that's a drift. So that drift probably gives you an opportunity to zoom over into a solution space much more rapidly. That is basically the idea. And once again, this entire thing is done repeatedly, and obviously you'll have some sort of a measure by which you would estimate whether a solution is reached or not. All of that will be there, done in a classical space. And normally this is used for optimization problems. Okay. Move forward, Prakash. We're not getting into the details of this. So this is what it also goes in. You have got one entity which combines one circuit which has got a problem Hamiltonian and another one is a mixing Hamiltonian. Both of them work together to create one entity of a circuit, and then you'll have multiple of them repeated p times. Measurement is taken. Optimization is typically done in the classical space, and then you identify how the variational parameters are going to be modified. These are the redefined variational parameters which once again flow back into the circuit. So that is how your QAOA also. Next slide, Prakash.
We can
very quickly I talk about QNLP. 2 slides. So here you can also use quantum. Let's say we can leverage on quantum algorithms for NLP. For example, you want to do some pre-processing. Normally, we use tokenization, stemming, stopwatch removal in classical NLP. And this is once again typically done in the standard classical case only. So your starting point typically will be having tokens. So you work on tokens. And especially if at all you're typically talking about LLM models and stuff like that, that is your starting point. These are basically where you start off with. Then there is a encoding that happens. And in classical NLP, you do word embedding. Okay, word to vector and BERT is what you use. How much or what kind of energy would sir, it all depends once again on the infrastructure and the availability. I'll just show you a small example. Yesterday I fired a job. It took more than 4.5 hours for it to compute. It took almost about 4.5 hours just to compute as of now, because it was typically running on a simulated environment on the Google Cloud. So all those factors, availability of that resource and network congestion and all of that typically probably came into picture. It took more than 4.5 hours for a very simple. I took an example of a housing prediction, housing price prediction. That is a standard example. So the same thing would have typically gotten done in about, let's say, half a minute on our standard machines. But the idea is, these things are still possible. We still do not know how really they do scale up. At least I'm not really done that sort of an exercise. But thank you. That's a wonderful question, sir.
Thank you, sir. Thank you.
Yeah. Okay. So there are a lot of challenges in QML, like hardware limitation. Algorithms are still not very effective. The problem is, we have algorithms, but still we do not have any means to find out how good they are working. We still do not have that sort of an opportunity. So we do not have any test beds or concrete use cases wherein we can test out these sort of algorithms. And we still do not know how good they train. So these are what are called training instabilities are there. So that is another issue. Scalability issue. We probably getting access to a 100 qubit, let's say quantum machine is going to cost a bomb for me. Right. So we got so many challenges that we still need to face. So current challenges are quantum hardware is very noisy. We have issues to handle about error correction, and large-scale quantum processors are still a few years away from made available as a public commodity. We still have to think about that. So people are working on alternate architectures, and people are thinking in terms of, is it possible for us to typically implement these quantum algorithms in a federated manner? right? I don't have to typically do at a single place, in a distributed like an environment. If at all I can do that, maybe I'll probably get some mileage out of it. And availability of real world commercial applications and people's acceptance, industry acceptance is still not that very good, even though everyone is going gung-ho about it. Next slide, Prakash. I think that should be the last slide, I think, from my talk.
This one or this one?
This one. This is done.
Ah.
Yeah, that's over.
Okay.
That's over.
Thank you, Professor Gokhale. And I think we had a good essential session. I will still record for some more time before we throw it in open. So one challenge is always, there are many challenges. One is, of course, business challenge, use case challenge, and specific domain specific. So each one of you, maybe Chintan, I start with Chintan. Chintan, tell us about the finance area. Where would you use such a quantum mechanism or QML types? Are you there? Or do I have to?
Yes, I'm there.
Yeah, go ahead.
Yeah, I'm there. Yeah, so definitely there are great use cases of quantum machine learning in finance domain, specifically detecting a fraudulent transaction at an economy level in real time. And that is where I foresee that QML would be helpful. Apart from this, I would say that QML, I'm not QML, but role of quantum as such in finance would also help us trade. Hello?
Fault detection and all that, right? Fraud and all that.
Yeah, so that would be for fraud detection and
credit card rating,
helping all the customers have a customized products. So right now what we are having is a generic product, but down the line we can actually plug and play and then design a product based on our dynamic ratings and new products. When interaction between machine, man, and algorithms increase. Like think of having a fleet of autonomous drones flying goods across the nation, and that is where you need to calculate the dynamic taxation as well as insurance part of the entire supply chain, and that is where quantum machine learning and quantum as a technology would definitely be useful.
So I would now ask one question to Ba. Ba, are you there? See, the machine learning, usually we end up in having explainability issues, ethical issues, and so on and so forth. So what do you expect in the quantum machine? Will it translate there? Or do you expect some changes there? Additional.
Okay. For quantum computing to benefit machine learning in some manner, for the time being, I haven't seen any work that says quantum computing would fundamentally alter the quality of machine learning, in the sense that, okay, if machine learning has explainability problem, just because you use quantum computing, it doesn't make the explainability problem just go away just because you use quantum computing. Now, there are quite a bit of work in terms of speeding things up or getting quantum computing to do machine learning at a scale that classical computing would not be able to handle at all. So in that sense, when it comes to scale, when it comes to shortening the time of doing the computation, yes, quantum computing can help. That would depend a lot on the hardware advancement being made to a point where these things become feasible. But in terms of solving fundamental questions of, can you somehow eliminate things like hallucination? Can you somehow eliminate things like, can you somehow make explainability suddenly easy and possible? I haven't seen work in this area that says, just because you use quantum computing, all this fundamental problem suddenly just becomes not a problem anymore. So there are still work to be done in those areas.
Excellent, excellent. So I would go to Gokhale now for one more. You have talked about PennyLane. What you can do with PennyLane, I believe we can do it with IBM Qiskit, which has the dashboard and you can drag and drop circuits and get the equivalent amount. And they also have support for many things. So is Qiskit. Qiskit may not be so graphical, but it is more performance oriented. So my question to you is, can we do anything better than PennyLane, or is it always ups and downs? How do you see the biases that happen to data, etc., and how do you handle that? Two questions basically. Are you there, Gokhale?
You're on mute, Gokhale, you're on mute.
Gokhale?
Okay. Yeah, I can. Yeah. Okay, so when you talk about Qiskit per se, Qiskit, the drag and drop option is for at the very, very beginning stage. Normally you once again use Python as the base core, and then you use the Qiskit library support for that. Now, whatever you can do probably in Qiskit, not that you cannot do in PennyLane, and the other way around. PennyLane has now become a little more of a, I said, quote unquote industry standard. Number one. Number two, the type of a model that it gives you, and it typically assigns, let's say, a function, a code block to be bundled with a device, and then you can just set up a orchestration mechanism so that each of these code block can be assigned to execute on a specific environment. So that gives you an opportunity to implement maybe a federated type of an implementation or a distributed type of a implementation. Those are something which are very, very popular.
So one just to stop there. What about open QASM 2.0, 3.0, and whatever the assembly level
No,
compatibility?
I don't until unless you actually get on to fine tuning about, you talk about errors, you talk about that thermal energy estimations and diffusion. That time when you want to really optimize, then only people typically go on to the assembly level implementations, right?
Okay.
Uh,
Yeah.
at a gross level, at a fine grain level, people go for assembly. At a gross level, people still stick to implementing the core in PennyLane or in maybe Qiskit. Both of them are acceptable.
Yeah. There are many cloud-based implementation, dozens of them. So
Very true.
what I would say is at this time, we will try to conclude just answering one question from our side, that is biases, which obviously I asked and both of you, and it means that if there is a bias which is existing in current machine learning, it doesn't go away in any way from the uh, quantum machine learning. And in fact, there will be operational problems for, like, we have DevOps, you have AI ops, you have ML ops, you will have QML ops, and so there will be plenty research area available. With that, I think I will thank our panel initially for all. Apology for the initial delays. First to having some issues in the what do you call the setting up of the panel, but apology for that, and hopefully we'll not do it in next time. So Ba, thank you for the excellent
May I say a
participation.
couple of things? May I add a couple of comments before we end this session formally?
No, I'm only recording. I'm stopping.
Oh,
We'll
okay.
follow the comments. See, I want to finish the recording. Any comments you want, we can do without recording. That would be better, I think, without having to expose anybody for anything, because you can ask even stupid questions. That is the way you learn. So never mind. So thank you.
These are meant for the general audience.
Oh, okay, sure.
Okay.
No problem. Do you want me to record it? We can
Yes,
continue.
please continue recording for the time being.
Okay.
And I
So
promise
go
to make this
ahead.
quick. Okay. So we talk about using quantum computing in the process of doing artificial intelligence and machine learning. Now, we haven't quite made a big difference in terms of whether we're using quantum computing for the training of the model, or just using the model for inference purposes. Now, for practical application, there's a big difference, especially now that people are doing a lot of generative AI. Training a model, everybody recognize, is a very big process that is very costly. And it's also the process where currently institutions with with large amounts of resources can muster to train really big models. And this is potentially where quantum computing might get in earlier just because of the resource constraint, right? You need a lot of resources to train big models, and only institutions with lots of resources currently can afford true quantum computing, right? Now, inference is a fairly different problem in the sense that you want inference to happen everywhere. In fact, you want inference, in most cases, you want inference to happen as near the edge as possible, even right on your handheld devices to do inference. Now, this is the sort of thing where it will take a much longer time for quantum computing, true quantum computing, to reach in those places, just because of many reasons. The very stringent requirements of temperature that we have for true computing hardware, for example. I mean, it'll take a while for hardware to advance to a place where you can actually do quantum computing at the edges or even at consumer devices. Never say never. But right now, we don't really have a straight line of sight that says, okay, given so many years, there's a way to put computing in every iPhone, for example. That's going to take a while. So this is one comment. And based on that comment, I want to point you to a webinar that we have planned coming in October timeframe. You see the screen right now. The first reference, quantum machine learning. There's an author, Samuel Yenchi Chen, who is a co-author of this first reference. Professor Chen, actually Dr. Chen, will be giving that talk in October, talking about how to train a model that are trained in quantum computing in the cloud into a model that can be executed by classical computing infrastructure at the edges, at user devices. So hopefully that talk will be of interest to audience here. So that's why I want to bring this up, because it ties this talk all the way out to the one that we plan in October. And for people who are thinking, who are also interested about the differences between training versus just doing inference, we actually had a talk earlier, just a week ago on August 7th, which again you can refer back to the working group web page and see the links to the presentation video and slides there. Where the speaker, Dr. Kim from Korea, talked about how to do quantum reinforcement learning with concrete examples and use cases on how to do this for learning, training the model versus just using it for inference. So thank you, Prakash, for giving me this opportunity to add in this couple of comments and tie it back to a past webinar as well as tie to a future webinar. Hopefully that will interest our audience here.
Absolutely.
Yeah, I think that's awesome.
And definitely I agree with Bob for providing the platform, because he has been the active one in taking on AI/ML as well as quantum. I appreciate all that. And plus, if you have any certificates are required, those who have, they may put their email ID on the record here. If you have registered, verified, and then whatever is done by the IEEE chapter, Bob, you may say about that, a quick certification.
Actually, sorry to say that this event hasn't been qualified for us PDA certification, so
okay, very good.
Really available.
So no certificates will be available. However, if you are looking forward to anything, having attended, having learned, if you have any question, please share with cloud24/7@IEEE.org, which is my email as a co-chair, or you can send it to chintan@ananthamsystem.com. We will try to address those. Hopefully that will we'll end the recording here, but at the same time we'll try to continue. If you have any questions, I'll stop recording first.